Okay, we are going to talk about the chapter 6, applications of definite integrals. First section we deal with volumes using cross sections. First we want to understand what's a cross section and how we get from this cross section to the volume, right? Because our title is volumes. So the title says we use cross sections to get to the volumes. First of all, consider three-dimensional object, because when we consider the volume, it has to be three-dimensional object. And then consider cutting this object vertically with a plane. And when you cut it with a plane, you get this blue plane in the picture. As you would see, this is the blue plane in the picture. You cut this S is the solid, okay, solid S. When we cut it with a vertical plane, then you are going to get an intersection area. This is an area, and we call it cross section, S of x, and it has the area A of x. Okay, S of x is the cross section, okay, and A of x is the area of that cross section. Our solid is defined on the interval a to b, for x in a to b, by the way. And our plane is called px because we build our plane at x. Okay. So let's remember how to find the volume of any object. The regular solids that we know of, for example, we have cube is a regular solid, we have a cylinder is a regular solid, and these type of regular solids, the volume is base area times height. Okay, and for the irregular solids, it's the same. For example, in this picture you are seeing a solid which is kind of cylindrical. We call it cylindrical solid, okay, and it has the base area. This A is the base area. This region is the base of the solid, and we just in order to find the volume of this solid, we just take the base area and multiply this with the height, and A times A is the base area, H is the height, so A times H. Okay, keep this in mind. Now we look at the same solid again. In this case, let's say we have a new terminology which is called slab, thin slab. Okay, thin slab you can consider, okay, a cylindrical object, three-dimensional object. It's very thin, and you can consider that we are consider slicing a bread. When you slice a bread, the slices are called thin slabs. Okay, and the volume is made up of adding up the volumes of these thin slices. Okay, so in this picture, xk minus 1 and xk are 2 points, and their distance from each other is not far away. And we look at the we have a plane, vertical plane that passes through xk minus 1 and xk, and we intersect this s with them, and we get the slices. The first slice is s xk minus 1, and the second slice, s of x, is s xk. And then if you consider the region among this, you get a solid, and this is the thin slab. It's a slice of this solid. Okay, what we are going to do, we are going to be able to calculate the volume of this object by just calculating the volumes of these thin slabs, and then add them up, and we get the whole volume. you can see the enlarged slab, thin slab here. So we have the xk minus 1 we expressed before, and we have xk here. So just consider this region. Actually, even if it looks very big here, it is a very thin one. Okay. And of course, this cylinder, this is an irregular cylinder. Okay. Of course, it is a base area. Okay. And the base area of this cylinder is AXK. Okay. And the height of this cylinder is delta xk, which is xk minus 1. And we are just approximating the volume of this, the volume of this cylinder, okay, by using this information. We are going to just take the base and multiply with the height. But I want you to observe that this base, if you take this part as base, AXK, it's not the same as AXK minus 1. So this is not a regular cylinder. But of course, when we are calculating the volume, we are going to just choose one of them and then continue from there. So that's why it's called approximating volume. It's an approximated volume. It's not really exact volume of this thin slab. Okay? Alright, next. Now, what's the relationship between this with the integrals? Actually, the volume of a solid, okay, of integrable cross-sectional area A of x from x is equal to a to x is equal to b is the integral of a from a to b. What does this mean? Okay, so this a of x that you had seen, these are the cross-sectional areas that we get. If you slice a bread, at each x you get ax, you get the surface of the bread, okay? And this is the cross-sectional area. And we have several x's. Of course, the bread is not a regular one, okay? Some parts could be thin, some parts could be thick, etc. So, these cross-sectional areas may differ. And then this dx, do you see that ax times dx? This dx you can consider as the height of this cross-sectional bread slices, okay? This is the base area times the height of the bread slice, and then you get a volume of the bread slice. And then you're gonna get a lot of those bread slices, which is the same as you are integrating from a to b. And then this sum notation is just you are adding them up. You're adding all the volumes of these bread slices. If you have 1 million bread slices, then you're adding them up. If you have 2 million, you're adding them up. Of course, here we are using Riemann's sum again, but we don't see it. So this volume is actually the limit of the Riemann sum of bread slices, volume of the bread slices, okay? So this is a direct result of that conclusion, so we don't get into the details in that. Alright, so how would you calculate the volume of a solid then? First of all, you're going to sketch the solid and get a typical cross-section. Well, how does it look like, the cross-section? And then you are going to try to find a formula for this cross-sectional area, okay? And you're going to determine the limits of the integration, and then you're going to integrate ax to find the volume. That's all you're going to do. So it's not really very difficult, okay? For example, let's say we are interested in finding this, the volume of this pyramid. First of all, it's going to start at 0 and it's going to go up to 3, the x values. And then a typical cross section is, thank God, it is a square, right? Because we know how to calculate the area of a square. At x, okay, at x, the sides of the square is x, alright? And then you just, the area of this slice is x squared, and as x changes, we are going to get bigger and bigger slices. That's fine. So we are going to integrate from 0 to 3, and alright, and then we are going to integrate that x squared dx and 0 to 3, and we are gonna get the volume of this solid. Okay. There's a wedge. Okay, let's try to understand that. Okay, so this is a wedge. Interesting picture, but consider that you can consider this wedge as maybe wedge, kind of wedge in your shoes. Okay, so we are gonna look at the first cross-sectional area. You just cut it into slices, but each time you slice it really in a reasonable way, and this slicing is good because you get rectangles when you slice it like that. And then as x goes to 3, I mean from 0 to 3, we have a rectangle. Alright, we have to, so how would you find the volume of this object, this solid? Okay, you're going to use this a of x, this rectangle's area of the rectangles, and you're going to integrate it from 0 to 3. Alright, at the very end, at 3, you are not, your rectangle is going to be just a line. Okay, do you see that? Line segment actually. Alright, and then observe that if for any x, of course we are taking this wedge is a special one, which means this is 45 degrees constant, it doesn't change. Okay, so for x you have the length of the width of the rectangle is x, and the width of the rectangle for each x, what's the formula for this graph is this, I think this is a circular, this one is circular, so for each x this distance is going to be minus squared root of 9 minus x squared because of the circle. Okay, the base is, if you consider the total base, it's the semicircle. Alright, and therefore it is if you consider the length of the rectangle, it is 2 times square root of 9 minus x squared in length. So now we can easily calculate the area of this rectangle, which is x times 2 times square root of 9 minus x squared. Now we are ready to do the integration. 0 to 3, x times 2x times square root of 9 minus x squared dx, and then you just integrate that and you get the volume of this object. Alright, so this is just geometry you have to be careful about. Okay, this is a nice example. There is this Cavalier's principle. It would make sense because we know what the volume is. Look at that. This is a regular cylinder. This is a little bit tilted cylinder. Let's say we tilt this part towards left and we get this part. And let's say we tilt this towards left again and we get the bottom part. And Cavalier's principle says they have the same volume. And it says imagine each solid as a stack of coins. Yes, really true, because at every level the cross-sectional areas have the same base area. Okay, and they have the same height. Okay, look at that, the heights are the same of the cylinders, so they have the same volume. So this is a really nice, interesting example. Next, we have another topic to talk about, solids of revolution, and we use the disk method here. First of all, we start with a region, okay, and then we are going to rotate that region about an axis in its plane, and we generate a solid. We call this solid of revolution because we are rotating or revolving a region, so therefore this is called a solid of revolution. And then we want to find the volume of such a solid that we generated, we created. And how would you find it? Again, first of all, we have to find out the cross-sectional area A of x. Okay? But this cross-sectional area is special because it's going to be a disk, since we are rotating a region. Okay? Because if you rotate a region 360 degrees, you get a disk. Okay? And therefore it's easier. So source of revolutions is easier to imagine. And then of course we are going to have r of x, which is, it's going to be the radius of the disk. Okay, a of x is going to be the area of that disk. Okay, which is actually pi times r squared. R of x is capital R of x. So this cross-sectional area is easy to find. So when you do a solid of revolution, since you are revolving a region around an axis, it could be x-axis, y-axis, z-axis, whatever, you're going to get the cross-sectional area as a disk, and then it's easy to find the area of that cross-sectional region, and then a of x becomes pi times r squared. R of x is what we described, okay, and the examples are going to make it a lot clearer. So here is the formula: volume by disks for rotation about the x-axis. If you have an x-axis, if you have the region to rotate around or about the x-axis, so your region is going to be r. Your region is going to have a radius r of x. Okay. I mean, you have to actually let me see whether we have a picture here. Yeah, the picture is going to be much clearer. Okay. Then your so volume is going to be a to b of x dx is equal to a to b pi rx squared dx. Let's move to the next page. This is much clearer for you, right? So this is the region that we want to rotate. This is a two-dimensional region, right? X and y. So we take a region, okay, and we rotate it. R is not the region. R of x is just a radius of that region at each x. And then just we fix an x, since we are rotating around about the x-axis, we fix an x, and then we rotate. And we just form our r of x. At each x we have r of x. And since we know the formula, the radius is square root of x, no problem. And then we rotate this region about the x-axis. If you rotate it, you get such a picture. Okay? And do you see that this cross-sectional region you get is a disk with the radius r of x? Okay? Then the area of this cross section is easy to find, pi r squared. And then we are going to multiply this with the dx. Dx is going to be the height of this little circular region, and it's going to be the volume of this. But if we integrate from 0 to 4, then we are going to get the total volume here. Okay, that's very nice. Here's the sphere. Look at the sphere, and here's the origin. The radius of the sphere is a. Okay. Let's consider we cut down this cross-sectional cylinder. Okay. And slab, actually, this is the thin slab. Okay. The height of this cylinder is delta x, very small. And the base area is approximately a pi times a squared minus x squared. You can calculate that. You're going to form a right triangle here. The radius is a of the sphere, and this is x, and the height, I mean this distance is going to be, in this case, r of x, is going to be a squared minus x squared. We need the square of that because we want to find the pi r squared, right? And so we find the a of x as pi r squared. R squared is a squared minus x squared. Okay, and then we just integrate that 0 to negative a to a. We are going to integrate because x changes from negative a to a. Okay, you can consider that this semicircle is just rotated around x-axis. Okay, this semicircle is x squared plus y squared is equal to a squared. That's the formula. You can use that. And then, which is this here, x squared plus y squared is equal to a squared. Okay, therefore r of x is square root of a squared minus x squared. And then we just use the formula, a of x is pi times r of x. R of x is in here. Take the square of that, you get that. And you just integrate from negative a to a, you get the volume of the sphere. Here's another example. So we have the left picture, which shows the region that we are going to rotate around y is equal to 1. We are rotating around y is equal to 1. And this is parallel to the x-axis. Okay? Kind of similar to rotating something around x-axis, but this is rotating something around a line that's parallel to the x-axis. That's fine. We just need r of x. We know the graph of that, y is equal to square root of x. R of x is equal to square root of x minus 1. Okay, this is r of x because this distance is square root of x. But this distance is 1. I'm interested in this distance. It is square root of x minus 1. This is my r of x. And I'm going to rotate this around y is equal to 1 here. When I rotate this, I get such a thing, such a solid. Okay? Like a bullet. This looks like a bullet, right? And then, so I'm integrating over x from 1 to 4. I need to find the cross-sectional area. I already know r of x. Pi r squared is the area of this region. Square root of x minus 1 squared, pi times that. And then pi, okay, a of x is going to be pi r squared, so we find that. So we integrate from 1 to 4 and we get the result. Okay. Now, instead of rotating regions about x-axis, we can rotate them about y-axis. What's the difference then? Nothing is really different. We are going to integrate over y. We are going to still integrate a of y, the cross-sectional area, from c to d. Okay, but in this case, the radius is going to be expressed in terms of y, r of y, pi r of y squared dy. Okay, so we repeat again, volume by disk for rotation about the y-axis. This volume is going to be integrating over c to d, a of y instead of a of x, and we integrate over y, that's why we have dy. And again, c to d, pi times, since it's the rotation, we have to have this area of the disk, pi ry squared dy. Okay? Here are some examples. Let's get the region A. And region A is going to be revolved around y. Look at this region, nice region. Okay? This is another regular region. That's fine. We are going to rotate it around y, and we are going to get a shape like this, very nice solid here. Okay? Now, I want you to look. So you're going to fix y now. If you're rotating around y, you fix y. If you're rotating around x, you fix x. When you fix y, you're going to look at the corresponding r of y on top of y, like this. And how would you find it? You look at this function, x is equal to 2 over y. At y, r of y is going to be 2 over y. And this is the radius that you're going to be rotating around, okay, about y. So when you rotate it about y, this y becomes, it creates this disk. You get this disk, right? And how about the area of this disk? is area of pi of area of y is equal to pi ry squared. Okay, pi times ry squared is 2 over y squared, which is 4 over y squared, right? So, and then dy, you're going to integrate over what's the corresponding y value. Y is changing from 1 to 4. So you just look at this picture and then create this picture visually to see. And then y is going to change from 1 to 4. Pi times 4 over y squared dy. You just integrate and find the volume of this solid. Interesting, right? But that's true. And there's another example. You see this region. This region is created by using the what's the formula for this graph is x is equal to 2 minus y squared. Okay, this is a parabola. The blue one is a parabola. And then there is this line. So we are going to rotate this around the line x equal to 3. So x equal to 3 is a line. It's parallel to the y-axis. So you can consider this as rotating around a line that's parallel to the y-axis, right? So your r of y is going to be a function of y. The idea is, what is this distance? What's the length? So how would you find it? Okay, so in order to find it, first of all, we want to know, okay, it is this distance minus this distance, right? This distance, okay, excuse me. So this distance is the whole distance minus this distance. So the whole distance is x is equal to 3, right? The whole distance is x is equal to 3. This distance is x is equal to y squared plus 1. Okay? If you take the difference, you get 3 minus y squared plus 1, you get 2 minus y squared. And now we have r of y. Once you find r of y, everything is easy. Okay, once we find r of y, we are going to say a of y is equal to pi times r of y squared, and then integrate it. Okay, and then you're going to find, at the end, you're going to find the volume of this weird solid. Okay, how about y? Y is going to change from where to where? Look at the y. So y is going to change. Look, y is taking values from negative square root of 2 to 2, square root of 2, I'm sorry, right? These are the y values that it changes from. So this is the minimum value for y minus square root of 2. This is the maximum value for y. So your integral is going to go from negative square root of 2 to square root of 2. Alright? That's it. Okay, we have another method. Not method, but other situations, I should say. Sometimes the solids that we have, they may have some holes in it. For example, there is annulus. There is like in the picture, okay, like this solid has a hole in it. So when you have such a solid, then how would you do? How would you find the volume of this solid? Actually, the idea would be find the volume of the outside, find the volume of the whole solid as if the inside is full, so no holes in it, and then find the volume of the inside, the whole, find the volume of the inside solid, and then take the difference between the two. And this is called actually washer method. Okay, so this washer, we call washer, is kind of annulus. Annulus means it's just this disc inside another disc. Okay, it's called annulus, but they call it washer. Okay, two different names, ANNULUS. Okay, so in this sense, if you look at this this washer, we have an outside radius. We have this big disc and inside another disc. So we have the inside disc has little rx, the outside disc has capital Rx. So all right, so in that sense, we have to consider finding the volume by using r of x, okay, and then finding the volume by using the little r, of x, and then just taking the difference between the these volumes. Okay. Okay, see, washers are not discs. Discs are, you know, the regular disc. Washers are disc inside another disc, but the inside disc is taken out. Okay, so the story is again similar, a to b, a of x dx, but what is a of x? So we need to find the a of x of this area of this washer. And it's not very difficult, because if you see it, okay, and this could happen actually, these type of washers is gonna come up. How? Let's look at the beginning. Okay, this is the first picture. So we have a function, capital R of x, we have a little r of x. These are two different functions. Okay, and then we have a region between a and b. Okay, this blue region. And at x we have this different r. You can consider this a function r, capital R, function little r. And then we take this and rotate this around x. When you rotate it around x, so this part becomes creates the hole inside the region. If you rotate it around, you get this. The inside is empty hole, and then you observe this washer here. Okay. Okay. So then, how would you do? The volume is a to b of x dx, then it's going to be equal to a to b pi capital R x squared, which is, it's the volume of the whole solid without no hole inside, and then pi r squared is the a to b pi r squared is the volume of the inside solid. So you are subtracting the volumes of solids from each other to find the solid that we created. Okay, so outer radius is r of x, inner radius is little r of x, and a of x is what? Pi r x squared minus pi r little r x squared, which you can combine like this: pi in parentheses capital R squared minus little r squared, and then you just integrate this a of x instead, and that's very easy. Okay, let's consider such a region. Look at this. This region is found. Okay, what's our origin? The x-axis. We have the outer, we call it outer radius. Outer radius is this curve. It's going to give us this curve, which is negative x plus 3. And the inner radius, which is little r, is going to come up from this curve, which is x squared plus 1. Okay, little r of x is x squared plus 1. Capital R of x is negative x plus 3. So we are going to take this region, rotate it around x. See, there's hole created in between. This hole, actually, afterwards, this such a solid is going to be created. And what is the washer? The washer is easy. This washer is seen like this. Okay, how it is created. Just try to look at this annulus. Look at this washer. Okay, and we have millions of such washer on top of each other, and then we get the whole picture afterwards. So outer radius r of x is negative x plus 3, inner radius is little r of x, x squared plus 1, and then we get the volume by just taking the squares of these radiuses, radii, and then multiply with pi, and then integrate from a to b. But what's our a to b? Negative 2 to 1, the x values. All right, here's another example. Look, this time we are rotating around y, not around x. Okay, so in that sense, our radii are going to depend on y, not on x anymore. All right, so what's our little r? Little r is going to be the graph of this function is what? X is equal to y over 2. And the graph of this, this function is y is equal to x squared, and we just convert it to y. X is equal to square root of y. So we look at this distance. This distance, little r, is just y over 2. And this bigger distance is square root of y. Alright? And we find it by ourselves because y is equal to x squared is given. And then we form our washer. Our washer is going to look like that. We rotate around y. And then the rest is easy because you integrate, interval of integration is going to be the y values. It's going to be 0 to 4. And then pi capital R squared minus little r squared. Capital R is found square root of y, so take the square, you get y. Little r is y over 2 squared, y squared over 4. And then integrate over y times dy, right? That's it.